Good morning everyone, welcome to the next session of this summer internship. So we have done so far, we were building ourselves for computational side of physics, and I think now we are well versed with that. We have a base to start with, and today we are gonna hit physics. We are gonna discuss hardcore physics, like what we do, what is equation of state, what is thermodynamics, what is Velishka model, what is mean field model. All those things I'm gonna discuss in detail, right? So as we discussed in our previous let me put myself in a center stage, probably in this file. Yeah. So what we were discussing is I shared you YouTube video, right? And the YouTube video is available on this website. Okay, so there are two YouTube videos on the same topic. One is in English, one is in Punjabi, and I ask you to go through this video, right? And I hope you have gone through all of that. So I shoot that video maybe 5-6 months back. Okay, anyhow, so let's start with the discussion session about it. We will be having some discussion if you have some question about the video, and after that I will share my screen through my iPad, and I will share some of the insight which you were missed, or I would like to emphasize again. I will talk about that, right? So let us open this for discussion session about physics. So let me start with this question, like were you able to comprehend, were you able to understand the video or not? Again, hands up, hands down. Please guys, everyone, please interact. This is the only way we can interact. And then okay, let's start with the discussion session. If you have any question, if you have anything you want to discuss about the video that you didn't understand or you did understand, which was new to you, okay, I'm gonna go one by one today, so you have to bear with me, right? So let's start with okay, Niyukti. Niyukti, I have a question for you. What was your experience about the video? What thing you learned? And what, do you have any question you can ask? Okay, let me start with the guys who are interacting first, and I give time to other people, but I will definitely talk to you for 5 minutes today, each of you. Okay, so Ashish is interacting. Ashish, why don't you turn your mic and video so that we can talk like virtually, like virtually.
Yes, sir.
Yeah.
Sir, I watched the YouTube video, but the QCD section, it was a bit difficult to understand, and its phase diagram.
Okay, the QCD phase diagram. Yeah, I got it. I wanted to show that to you here. Okay. Okay, that's good. Okay, Ashish has a comment. Very well, thank you. Okay, now I will just follow this hierarchy here. Arjun, what about you? Did you go through the video? Do you have any question? Do you have any comment?
Hello, sir.
Hi.
Am I audible?
Yes.
Yes, sir. I have gone through the video and I have a doubt. So I have the same doubt. So in the pressure versus density graph, so you have shown that at the low density we have effective field, we are using effective field, and in the high density we are using perturbative QCD.
Okay.
And in between we are using various models. So the part I am missing is, so in the video you have mentioned that we are using a pressure of core at maximum and pressure of core at minimum.
Okay.
So I could not get that part. And the part you have told us that how it is related, how we are calculating the M.R. curve from the pressure and density curve.
Okay.
So in the video you have explained that we will take a point, we will take a density point, and then we will calculate its mass and radius, and we will get the points. Then we will plot it.
Yeah. Okay.
So I'm missing that part.
Okay, I get it. Thank you for your question and comment. So this is a very basic and in layman term video. So I just pointed out some shallow things there so that everyone can understand. So when we are gonna do, we will try to construct a TOV code, which is hard. I would not say it is easy. It is itself a research task. I will try a minimal example which can explain a basic case, okay, but we will use some open source TOV solver from users, right, to solve our equation of state. But I will walk you through like how TOV solver works, what's about the TOV equations, like how do we put pressure and energy density there and we get mass and radius. So we will be eventually talking about that in maybe after few sessions, maybe one or two. Yeah, so let's wait for that. Okay, Harish.
Hello, Dr. Rajesh.
Hi.
So I was going to ask you the same thing. As in, whether we will be solving EOS alone or will be applying it on TOV also to get mass radius.
Yeah, so again the answer is we will be generating the equation of state from mean field model, Velishka model, and then we will try to construct a TOV code like a basic one. I will not say it will cover all the physics, it will represent the most ideal, I mean very close to the real result, but then we will rely on some open source TOV solver which we can like put our equation of state in and it gives us the output, right? So we will do that.
Okay.
Okay, then Harveer.
Hi Rajesh.
Hi.
I'm sorry to say I was not able to saw the video because I was at work today. So most likely I will see the video in maybe this Sunday. So if I have any doubt in it, I will write to you.
Okay, thank you very much, Harveer. Thank you for your honesty.
Thank you.
Honor, what about you? How was your experience? Any question or comment? Can you hear me, Honor? Okay, maybe he is not with us. I cannot talk here. Okay, it's fine. You can write. If you have any question or comment, you can write. You can use chat. So meanwhile, we can go ahead. Kunal, what about you? How are things going on? What about the video?
Hello, Dr. Rajesh. Good morning.
Good
So
morning.
I have went through the video. Like I could not complete the whole video. I have gone through the video. I have developed certain understanding of what I could get, and I have one question apart from like a very general question about neutron star that I have. So there is this pulsating model of neutron star that we talk about, right? So how that is useful to like measure the mass and the size of neutron star.
Okay.
So as we have different methods to to analyze astronomical objects. So how do we do it with like neutron stars specifically?
Okay, I get your question. Thank you for your question. I will answer in 15-20 minutes.
Rest I have a certain part of that video remaining to watch, so I'll watch it.
Okay.
Then,
Okay, very well. Thank you. Niyukti? I guess Niyukti is not with us. Due to heavy rain, network is unstable. Okay, you can always use the chat. Then Rajesh, which is me, I can skip him. Ria.
Good morning, sir.
Good morning.
Sir, for the starter, I'm very confused about the basic difference between weak and strong nuclear force. I'm still confused.
Okay.
And I want you to explain the tidal deformability. I could not able to comprehend it clearly in simpler terms.
Okay. Okay. Thanks for your comment. I will go through that in some minutes. Shweta.
Hi everyone. Actually,
Hello.
I have doubt about the elementary particles. Like neutron stars are made up of which one of these particles, or something. Can I write? Actually,
Yeah,
can
yeah,
I please?
yeah. Okay. Okay, Yadav, what about you?
Good morning, Dr. Rajesh. I was curious. I have little out on the equation of state and TOV equation and Q series phase diagram. So, can you explain it again?
Okay, I will go through that part again.
Thanks.
Thanks. Okay, I will wait for Shweta's comment before moving on. Okay, that's glad you have gone through the video. So I'm very happy. And I will share my screen in a bit, and then we will go through the parts where you have questions. Let me stop my screen sharing here. Okay. I was little confused about elementary particles, like how they form the structure of neutron star, and how did we identify that, Okay, I will answer you. See, I will go through the entire presentation one by one, and I will kind of try to remember what question you asked. If I remember, I will answer. If I miss some of your question, please point me out before moving on the next slide. Okay, so let me just put my computer screen so that it has the most of the iPad screen. Yeah, it cannot have, but okay, we can bear with that. Okay. And Ashish, you also asked me about my son experience. I will tell you. I will tell all of you at the end of this class. Okay, so here we go. See, this presentation, this was a colloquium, and the title was From Microscales to Macroscale, Understanding Neutron Star via Nuclear Equation of State. Okay, from the title itself, it is very clear that we are connecting to different regimes. One is microscale and one is macroscale. When I say microscale, I am talking about equation of state, like pressure, energy, density, temperature, which are the microscopic properties of a matter, right? And when we talk about macro scales, I am talking about stars, astro, sun, all those things which are gigantic. Okay, and in that case, the properties, the microscopic properties we are more interested in is like mass and radius, right? We are trying to connect those. Now the fundamental question arises, which I guess Shweta or Ria asked. Okay, Shweta probably asked that how do we know what is inside a neutron star, right? So we don't know, and any experiment, we can do any experiment, but we will never know, because they are very far. We can only guess through the theory, and we have the power from the theory. We can try different equation of state with different composition of particles with different degrees of freedom, and when we do that and we model that thing and we put the equation of state to the TOV solver, which also have some assumptions, right? TOV solvers have different versions. Some of them have this assume that the neutron star is not rotating, so the rotation does have the effect on the mass and radius, which is very true, but we have like limited cases, and we always ignore magnetic field. If you remember that we are doing our calculation at b is equal to 0, but in reality neutron star have like gigantic magnetic field around 10 to power something Gauss, 4 Gauss I guess. Okay, so which is very very high. So so what we are doing is we are trying to simplify the system. We are trying to do the minimal thing and try to explain the system. Okay, so let us start with this. So summary, all those things. So I don't want to go through Big Bang. I just wanted to point one thing out. So this is the regime here, which is a macroscopic regime, which I have divided, where the physics, the fundamental physics is governed by microscope mainly. I would not say at all. So these are the thing where the particles were like interacting with each other at the very microscopic level, like strong interaction, weak interaction were dominant at this place. But here when we talk about this, after this hadronization phase to the main phase where all the galaxies form, the current shape of the universe formed, where we have enormous galaxy or astrophysical bodies, right? In that case, in this particular regime, although there are forces like microscopic forces prevailing in the microscope level, but we see the universe as a macroscopic thing. We see stars, we see gigantic bodies, sun and earth, all those things, which are the first force that comes into our mind is gravitational, right? And looking at those gigantic body, we can see, okay, the main force that dominates is maybe gravity, which is not true, but it is just an illusion, or electromagnetic, because we can see light, right? So this is the part where we are more interested in the macroscopic properties of the particle, like the shape, size and all those things. So this is how I have divided this. Okay, I'm not gonna go through the entire slide. So I will just go to this slide, and I can remember one question from one participant, that what is the difference between nuclear and strong force. Okay, so one thing is like I would like to emphasize, these three forces have a quantum mechanical nature, right? It has a QED. Okay, QED, let me write the quantum version of electromagnetic force, which is QED. Nuclear force is itself a quantum force, weak force is itself a quantum force. When I say quantum, you can change it with micro, right? And on the left side we can see we have a different, why we needed two different force at the microscopic level. Okay, let's forget about this, only these two forces let's talk about. So why we need two different forces to act within the nuclei or atomic level? So because their roles are different. Why we need a nuclear strong force? Because we want to explain how two protons can stay together, because electromagnetically plus repels, right? So we have no explanation that since neutron is neutral, why the nucleus is still stable. The only explanation is there is another force which is keeping the two protons together, right? And it is 10 to power 2 order of magnitude powerful than the electromagnetic force. That's why it is keeping that. Okay, and then we have this potential energy curve with respect to internuclear distance, which is the representation of a nuclear or strong force. And why it is called strong force? Because it is the strongest of all. And you can see this is a very famous curve, right? You can observe it in atomic level, molecular level as well. So this is a property of a strong force, that when the two nuclei are very close, let us say any any particle that participates in nuclear force, right? Then whenever they are very close, they feel repulsion, right? So this is a positive curve here. But whenever they are going apart, okay, the internuclear distance is increasing, then they hit in minima, okay, and then again start increasing, and it never reaches the zero, okay. So the most of the part the strong force is attractive, but when they are very close, then the two particle experience repulsion, and due to that repulsion there is a pressure setup, and we call this pressure as a Fermi pressure, okay. So it is a very important term that will be used in while defining equation of state, not defining equation of state obviously, and discussion through the TOVs. Okay, so this is about a nuclear strong force, and it acts at 10 to power minus 15 level. But nuclear force cannot explain like why there is a radioactive decay, why heavier nuclei tend to break into lighter nuclei. For example, let us say uranium tend to krypton or something X, I don't remember, but uranium breaks 235 or 298, it breaks by itself, like it disintegrates by itself. That thing cannot be explained by nuclear or strong force. We need some other force which can explain this, and the at that time, I guess Fermi theory of beta decay, right? Yeah, gamma theory. So gamma and Fermi, gamma also discuss about radioactivity and Fermi. So Fermi basically introduced the theory of beta decay and through the radioactive force, and the name of that force is called weak force. And weak force, if you don't have to stick to the name, the names are weird sometimes. Weak force is not weak amongst all those forces, it is just a weak force in comparison to strong force, right? And electromagnetic. So weak force, again it describes the radioactive decay of the particle which are in heavy A number, which have a heavy A number. So this is the one difference. And so we don't have any quantum theory of gravitational force, but since we are scientists, we love symmetry, we see nature, we want to see nature through one lens, right? We want to think that the nature originated from one force because of the symmetry, and we have a strong evidence that for this guy we have a strong evidence, not strong evidence, it is a fact that electroweak theory exists, and these two forces were together, right, at some point of time near the Big Bang, and this is very well established fact. And later on we saw that okay, there is a grand unification theory, electromagnetic weak force and nuclear strong force can also be combined through the standard model, right, which explain these three things. But these things are not properly coupled in a way like these two are coupled. And the electroweak force was given by, the theory was given by Abdus Salam, okay, Abdus Salam, very famous Pakistani scientist. And then we have Glasgow, okay, we have three scientists which shared this prize, Nobel Prize for this discovery. Salam, Weinberg and Glasgow, yes, and Weinberg is a very excellent scientist. Okay, so now I'm talking about gut, I was talking about gut, grand unification theory, this. But what about the theory of everything? Theory of everything is when we have a single force that can explain all the fundamental forces. That means we have to include this guy here to these force. But the thing is, we know that universe is like, if you ask someone what is the true nature of universe, is it quantum or is it classical? Obviously it is quantum, right? So because the quantum forces are the one which prevails, which is giving the shape to the universe which we see through the naked eye. So we need a quantum description of every force, like which should be a fundamental differences between the forces itself, and also the fundamental description of the force. So electromagnetic force has QED, strong forces, quantum in nature, weak force is also quantum in nature. What about this guy here? Do we have a quantum version of it? Yes or no, guys? Okay, when you raise a hand, do you want to speak? Kunal?
actually I was trying to react, but
Okay, you can use that then, that emojis.
Yes, sir. There is quantum gravity.
Yeah, so the gravitational force doesn't have any quantum version so far. So we are trying to look, scientists are trying to look for that. They are describing, they are relying on different theories. For example, they are focusing on string theory, and there is also loop quantum gravity calculations going on, which can try to explain the quantum version of the gravitational force. If we have it, we can explain various problems in physics which are very prevalent today. So, so this is the piece of puzzle which Stephen Hawking tried to put, and he put that in his book Theory of Everything. I think I have it. Yes, I have it. Yes, this is a very good book. I'm not gonna go to that book, but okay, that will distract me from this. And another thing I wanted to tell you is that mediators are very important. Whenever we are talking in terms of a quantum level force, like which can be described through quantum field theory, or quantum electrodynamics, quantum chromodynamics, or electroweak theory, okay, then we know we don't talk in terms of particles anymore, we talk in terms of field, okay. And there is a field for every corresponding force in the universe, like we have an electric field or magnetic field for a magnet, okay. And but at the quantum level, the picture which quantum field theory tells us, that there are a field for every force, and for every particle in that particular force, which the particle participate in particular force, has a field, okay. And the particle itself, like for example, we have a spinor field which is electron field, and the particle itself, okay, let me draw here, I think it will be easy. So we have field, okay, you have to assume, you have to imagine it, it is an electron field, and whenever there is an excitation in the field, I will represent it through like this diagram here, okay, this symbol, and this electron, the particle itself is the excitation of the field, right? This is how we relate. And the field interacts with each other, like spinor field interact with other muon field, kaon field, pion field, whatever particle you say. So the excitation or de-excitation of these particles basically interact with each other through, and it can be explained to quantum field theory, which is a huge subject in itself. So I'm not gonna go there. So basically we are more interested in how particles are created and how particles are annihilated. So if you want to know more about it, I will share a very good YouTube playlist by Dr. Physics. He has explained it very well. Okay, so let's go further. I hope I was able to answer your question about difference between nuclear and weak force, right? Good. Now I will not talk about that. Somebody asked me about particles, elementary particles. What was the question? Okay, I think it is self-explanatory, the diagram itself, you can watch the video always. Then we have a Large Hadron Collider. You didn't ask me anything about that. I hope it is very clear. And I would like to emphasize one thing here, right? So what we are doing in heavy ion collision, in Big Bang theory, when we talk about, we assume, I mean, we have no evidence that what happened before Big Bang, we cannot know, but we believe that there was a Big Bang out of nowhere, right? Singularity, something popped out of nowhere, and from that there was a huge enormous energy, and with the area expand, it gets cooled down. When it cooled down, you know, simple thermodynamics law, if you have a temperature at a certain area and you increase the area, the temperature will distribute throughout the expanded area, right? And same thing happened. We try to create the same thing in through heavy ion collision, and we also call it reverse Big Bang. So what we are gonna do here, we collide heavy ions. What are heavy ions? The name is weird okay, but heavy ions are like just high A number nuclei, okay, high A number nuclei. It could be lead, it could be gold, okay. Why we want to collide heavy ions? Because we want to collide a bunch of particles with each other, and we want to accelerate it to 0.99 c, because we wanted it to be having a very high energy which is associated with the speed. And why it looks like that? a single thing? Why it doesn't look like a spherical or something, which is how we usually represent a nuclei? Because they are at a relativistic speed, and when the particles at relativistic speed, from the lab reference frame, they appear like they are Lorentz contracted. That's why they appear like this. Okay. Now they collide with each other since they have very high velocity and they have like particles and they are strongly interacting. When they hit each other, the temperature rises very quickly, and that particular temperature or energy, the constituent which were like atoms before, like lead nuclei or gold nuclei, like which they melted down and they form quarks. So from this particle picture we can see baryons, or let us say nucleons or hyperons, let us start with nucleons, which is like proton. So proton has internal structure quarks, which are elementary particles. So when you heat proton, when you give enough energy to the proton and when you confine it, it melted down into quarks, which is very simple observation. Okay. And quarks becomes asymptotically free, which is a fundamental property of QCD. We will talk about that in QCD phase diagram slide. So when they hit each other, due to the high energy, this breaks down into its constituents, and we call it quark gluon soup. Why? Because the hadrons turn into quarks, nucleons turn into quarks, and quarks are interlinked to each other. Why? How? They are interlinked to each other by gluons. So the gluons are the mediator. So they form a soup. Why we want to call it a soup? Because this is more like a plasma thing, right? This is the liquid, this is a fluid. When we talk in terms of fluid, we give it a fancy name. So we call it quark gluon soup, and also fireball, because it is has a high temperature. And then we have a collective flow. Collective flow is the process where it acts like a perfect fluid, okay, with zero viscosity. Okay. And then eventually, since the temperature is going down, area is expanding, what will happen? The quarks will lose the energy and it will again try to go in the previous state, which is a bound state. Okay. So from here to here, hadronization process, what is happening? The particles within this are colliding with each other, like chemically or kinetically. What do I mean by chemically? When they are interacting chemically, they are changing from one form to another. Maybe pions are changing to electrons or something to some reactions. And when we talk about kinetically, they are just hitting each other, but they are preserving their original form. Okay. So there are two type of interactions there. So eventually we have kinetic and chemical freeze out, where they are not interacting chemically and they are not interacting kinetically. And at that freeze out, the quarks and gluons basically turns into bound state, and they reproduce like different particles which can be detected in the detectors, high energy detectors. So I have not put any information about detectors. I am not an experimental physicist, but if you want to know, you can read about CERN. There are 4 detectors for various purposes. Okay. So whenever there is a recombination, whenever there is a, yeah, Harvi, you have a question?
Yeah, I mean, I don't know this is a question, or I just want to ask about the title, Reverse Big Bang. It looks like a Big Bang in terms of pictures, but why it is Reverse Big Bang? I don't understand that. Maybe due to the first 2 pictures, like where the gold and the lead particles are interacting, or I don't understand the title.
Okay, yeah, I get it. It is a very common observation. So it is a Big Bang. Okay, you are doing, when we talk from here to here, it is a Big Bang. Like it is something came from somewhere, right? Something came from somewhere and it is creating something. But why we call reverse Big Bang? Because if we have this guy here, we are making this happen. Okay, for this 2 part, I will say it is a reverse Big Bang, because we already have the particles in a hadronic state. Okay, and we are colliding those particles in a hadronic state, and we are making it into a quark gluon plasma state, which is in Big Bang it is this way or this way. So you are very right. Okay, for this part this is a reverse Big Bang, but here it is a Big Bang. Okay, So I was talking is like whenever there is a freeze out chemically, kinetically, the particles, new particles are appearing here, right, and they go through the detector, and due to various detector methods, all those things, you know, statistical analysis, we put some significant data analysis and we got to know that okay, this particle is this. Okay, so I'm not going to talk about that. So the thing is, what we are interested in this particular setup is how strong interactions interaction is happening at this level, because you know, quark gluons, plasma, nucleons, they experience mainly the strong interacting force. We are not more into gravitational force here, maybe electromagnetic, yes, but not in the weak or gravitational force. So we are interested in this system, we are interested in the thermodynamics of the system. Obviously, what parameters are interested to you, you can see directly. So when we are talking in terms of fluid, what parameters, what attributes of the system comes to our mind, which is temperature. What is the temperature of the system, what is the volume, what is the pressure, and what is the energy per volume, right, which is the energy density. So we are interested in that. So this is a very important slide which tells us that whenever we are discussing strongly interacting particles, we are more interested into the thermodynamics of the system. And when we call about equation of state, okay, EOS, let us say, equation of state is nothing but the relationship between these variables. It could be temperature, volume, it could be volume, pressure, it could be pressure, energy, density, or any case, you know, any combination, any permutation of this, whichever quantity we are interested in. Okay, so this was the diagram, like two of you asked me. This is a very important diagram, guys. So I'm not gonna talk about water diagram, but I will focus into the right. So we will try to relate this this diagram here to this thing. So there are two phases, guys. One is a deconfinement quark phase, which is here. Okay, what does that mean? Like, we had hadrons first, then it melted down to quarks. Okay, when it melted down to quarks, we call it deconfined. Why? Because the quarks are not confined anymore, they were confined in hadrons. So we know there are two properties of QCD. One is color confinement, second is asymptotic freedom. So what is color confinement and what is asymptotic freedom? When the quarks are inside a bound state, for example nucleon, like we have proton, up up down, so then they are experiencing color confinement, and whenever you try to pull two quarks apart, they will create a system so that the proton remains intact. Okay, you can get this information from a meson. When we try to pull these two quarks apart, another quark pair will appear so that it preserves the bound state. Okay, so this is the property, color confinement of QCD, quantum chromodynamics, or strong interacting force. And second one is the asymptotic freedom. Asymptotic freedom is the property of QCD which a strong force experience when the particles are asymptotically free. Okay, for example, in this setup, when the temperature is very high, the quarks are free, they are not bounded, they can travel anywhere. Okay, they have no restriction, and in that case we have asymptotic freedom property prevailing. But here again, when they form bound state, or here we have what, color confinement property. So we have two different kind of properties of QCD, and we are gonna learn that from the right side, which is the quantum chromodynamics phase diagram. So what is a phase diagram? Which tells us about different phases and the phase transition itself. And I have represented it in terms of equation of state because I have shown two variables here, temperature and baryon chemical potential. So okay, so let us talk about this diagram. This is a conjecture. Conjecture is an anticipation, this is not truth. Okay, this is, we are still exploring it. We don't have any significant experiments till date which can explain this part of the phase diagram, that's why it is a conjecture. Okay, anyways, so let us talk about baryon chemical potential. What is that quantity? Okay, I can think in terms of density, I can think in terms of temperature, pressure, energy density. What about this guy, baryon chemical potential? See, baryon chemical potential is the potential which is written by mu b, and it tells that given a chemical potential, how many particles and antiparticles can be created. Okay. So, it is a potential or it is an energy which at a given point can tell us how many particles and antiparticles can be created. Okay. And if baryon chemical potential, okay, let me write here mu b, okay, how many q and q bars can be created. Q is any particle, let us not confuse it with q but p, but don't confuse it with proton only it is for any particle. Okay. And now if mu b is equal to 0, then that means equal number of particles and antiparticles, and if mu b is greater than 0, then particles are more than antiparticles, okay, and vice versa. If mu b is negative, then antiparticles are more than particles, the number of antiparticles are more than particles. So, this is how this guy controls, and we are mainly focused in 0 to 1600 or 2000 MeV of baryon chemical potential, which is the range where strong interaction physics dominates. Okay. And the temperature we are interested in is 0 to 200 or maybe 300 MeV. Okay. So, neutron stars at effectively 0 temperature. When I say effectively, sometimes you might have seen T is equal to 0 MeV. You say whenever you explain neutron star, the neutron stars at T is equal to 0 MeV, which is absurd, right? Neutron star has temperature, it is like 10 to power 4 Kelvin or something, but when we talk about in terms of MeV, it is very low. Okay, then we can just simply say that it is effectively at 0 MeV. So, that does not mean it is at 0 MeV. So, similarly here we can see this particular area in the QCD phase diagram. Since we know one question that arises in our mind is why neutron star should have only strong interacting particles, why it cannot have any other force prevailing. The answer to that question is that neutron star is very compact, like you put how many 10 to power 17 kilogram per meter cube in just 10 kilometers, right? You squeeze your earth and you make it like 10 kilometers radius, and you can anticipate how densely you have packed your material. And what is the densest matter we can have, which force can provide you the densest matter? Only nuclear strong force. Okay, that is why you have this QCD phase diagram, and whenever we talk about 0 MeV thing, we have this range where the neutron star physics dominates. So, that is why this section is dominated by neutron star. And why only this particular section? Because we are only interested in the part where the density is very high. The more the chemical potential, I told you, the more the density of particles as compared to antiparticles. Okay, here we are increasing the density. So, neutron star range here. Okay, and we talk about when we go up in the temperature, we have neutron star mergers. Why neutron star mergers are there? Because neutron star mergers have some finite temperature, it goes from 10 to 50 MeV. So, this is the range where neutron star merger physics dominates. Okay, now let us not go to these particular section, but before let us discuss about color confinement and asymptotic freedom. I hope I am not talking very fast. Okay. So, this is very important, guys. We have to understand that QCD phase diagram is a diagram that shows different phases, and the two main phases we are interested in is the hadronic regime and the quark dominant regime. So, hadronic regime is the regime where hadrons are present, and hadrons are nothing but the bound state of quarks. Okay, we have up, down. So, I have only represented proton here, but you have to understand it covers all the hadrons. Okay, and it has hadron dominated phase here, hadrons, and then we somewhere we have liquid gas phase transition, which I have not shown here. Okay, let us not talk about that, I will overwhelm you. But let us talk about the main QCD thing, which is color confinement. Obviously, when the quarks are confined inside hadrons, the property that prevails is the color confinement. The color, that is quarks have color, chromodynamics, it is confined inside hadrons. That is why it is showing a color confinement property. But when we increase the density or temperature, when you squeeze your particles, the area is shrinking and you have enormous energy there due to temperature or due to squeezing. What will happen? The hadrons will break down into quarks, and when they break down into quarks, they lose their identity, they are no hadron anymore. And in this regime, then quarks can exist freely, okay, and then they show this asymptotic freedom property, they are asymptotically free, okay, and this region is called deconfined quark region, okay, or you can say quark confinement or deconfined matter. So, this is a confined matter, this is a deconfined matter, and here you can say quark gluon plasma, you can also say in other words. And there is a phase transition around 1200 MeV, let us say, it is not fixed, it is a model dependent thing, but we assume it is around this, and there is a phase transition which leans towards the temperature axis like this, and it stops at this point, okay. As we have water phase diagram, like we have solid to liquid phase, and we can see this is a phase where, what is the phase line, phase boundary? The phase transition line is a line which gives a strict boundary to both of the phases, like at this particular line both the phases can coexist, right, they can coexist here, but after that it is completely deconfined quarks, and before that it is completely hadrons, right, confined region. But this goes through all the way up to a certain point, okay, and it stops, and when it stops we call this particular point a critical point, okay. Let me put a critical point here, critical point. So, we have a critical point example here like this. So, we have a liquid to gas phase, like there is a strict phase boundary here, like it is liquid and sudden it is a gas. But when we talk about critical point, when it reaches the criticality, then it is a second order phase transition. Let us not go with first order, second order phase transition, but here after the critical point we have something called crossover. Crossover is a region where both of the phase can coexist, not just on one line, but through the entire region. So, this region is the region where both the quark gluon and hadrons and nuclei coexist, okay, and this region is experimentally verified. This region is pretty much experimentally verified. Do I have a different slide? Oh, I didn't put it here, okay. So, this region has a this region has a crossover behavior, right. I have another slide, I will give it to you. So, so this region is the region where the physics can be described by the current heavy ion data. The region of this temperature and baryonic chemical potential or density, the physics is already explained by heavy ion collision data, but so far they have not found any critical point, okay. But we do strongly believe there is a critical point, okay. Let me just go through the internet because I wanted to show you something. Okay, where is my plot? Okay, I'm almost there. Okay, so this is another view of this plot. Okay, and here I told you the baryon chemical potential is on x axis, and on the and in this plot it is represented in the baryon chemical, not baryon chemical potential but baryon density. So the baryon chemical potential increase, that means the density of baryons increase. Okay, so we can think in terms of baryons, or you can think in terms of chemical potential, density or chemical potential. So this is the same diagram which tells us that currently which part of QCD phase diagram can be explained by which particular theory. Okay, so this tells me that okay, whenever we are more interested in very high density and very high temperature, this is the rough plot, right? So this curve is not known, this is a rough plot for a demonstration, but we are sure that at this area perturbative QCD is the theory which can explain physics, and here also which can explain physics. Okay, it has a very strong evidence to support the experimental claim, the theory itself. Then we have lattice QCD. The problem with QCD is that QCD has two natures, like it shows deconfinement somewhere, it shows confinement property somewhere. So when we talk about confinement properties, like deconfinement properties, when gluons are free to move, then we have perturbative QCD, and it is very easy to calculate. Not easy, it is very hard obviously but it is very easy as compared to exploring this regime, because whenever we try to explore this regime through perturbative QCD, the coupling constant becomes very large and it hinders the calculation. Okay, it gives a hard time for perturbative QCD calculations. So perturbative QCD cannot be applied in this area, but then we have to rely on some other non-perturbative techniques. Okay, because this area is mainly for the perturbative region. Okay, perturbative dominated region because of the high density and high temperature, but here in the low temperature and low density, this area is more for non-perturbative regime where color confinement property is prevailing. So it can be explained through obviously heavy ion collision. Okay, experimental part. So heavy ion collision so far can reach up to 50 MeV to the BES program, and density up to, let us say, 2-3 times saturation density. Okay, right. So it can explain that region, heavy ion collision. It can gives you various data like okay, what is the collective flow, what is the rapidity, all those things. But in the, if we talk about a theoretical side, lattice QCD is the powerful tool, powerful theory which can explain the physics here, which can describe the equation of state here at finite temperature and moderate density, the green thing here. Okay. Now, but again, if I put a rough QCD phase transition line here, okay, I have not put, but because the purpose of this plot is something else. If I put, then there is a critical point, there should be a critical point, but so far lattice QCD hasn't observed this. Okay, and also experimental particle physics has not observed it, but we strongly believe that there is a critical point. So scientists are trying to extrapolate lattice QCD to that region so that it has a critical point, and experimentally we are also trying to do very hard. But the thing, the positive thing about that is, from lattice QCD we can trust this theory, and from lattice QCD we know that below 135 MeV there is no critical point. That means we have something where we don't have that thing. Okay, that is something promising, which can tell you which areas we can explore to find criticality. Then we have in the lower part, when temperature is low, how do we define equation of state there? How do we define temperature and physics there? All those things. We have chiral effective field theory, which is built on nuclear interactions, pion interactions. Okay, chiral perturbation theory, and this can explain physics in this regime. And then we have experiments, low energy nuclear physics experiments like binding energy, symmetry energy, and all those things, which can explain things here. Okay, and in this regime we can know experimentally thing and we can fit our models there. Now this is the neutron star regime, just the line. Why? Because the temperature axis is very small, the ticks are very small. Usually it should be like 0.1 to 0.001, okay, this, but here it is just a line because the scale is very high. So neutron star goes around 8 times nuclear saturation density, which is 8. Okay, this is the regime where the physics can be described in terms of neutron star, and you can also put a more, plot. Let us say like this. So if I do that, this particular regime is for neutron star merger, BNSM, binary neutron star merger, because it is at finite temperature and the neutron star merger go around 50 MeV. Anyways, so these are the various region in the QCD phase diagram which can be explained by various theories. So there is no single theory which can explain everything, which is a drawback, but I would say it is not a drawback, it is an opportunity to explore the nature, okay, because nature is complex. And now what about the white spaces here? So there is no theory which can explain, no fundamental theory, these are fundamental theories or experiments. So there is no fundamental theory which can explain physics here. So what do? We need to rely on some models. There are several models. I will only talk about mean field models. So mean field models are the model which can helps us to explain the thermodynamics in this region, right? In this particular region also, this it can go anywhere. So what we do when we say model? There is a difference between theory and model. What is the difference? The difference is model is, okay, the model relies on some assumptions, okay, and it should be calibrated to some theory or some experimental results. So the mean field models are calibrated on low energy nuclear physics properties like nuclear saturation density, binding energy, symmetry energy, which can be easily experimentally calculated. We fit our model to that property and then we extrapolate what will happen if we go in high density or high temperature, and if they support our result, like in perturbative QCD regime, in neutron star regime, in chiral effective theory regime, in heavy ion regime and LQCD regime, we say that our model is successful. Although they are fitted to that, but still they can explain all those physics. We say okay, that is a good model which can explain physics, right? So what is missing in this slide? Okay, I think I covered it all. Okay, before going further, I will pause for 1 minute if you have any question for this QCD phase diagram. Okay, you don't have any question, let us move. So I hope you were able to relate that. Somebody asked me about pulsars. Okay, I will cover it here. Okay, so let us talk about that. By the way, I would like to advertise my paper here. This is a review article. It has everything about nuclear strong interaction physics constraint. Like how do we know what are the various constraint? What is constraint? You know, right? Constraint are the observation that are benchmarks, right, which we can rely upon, whether it is theoretical, whether it is experiment. So we have put like all the constraint from various theories, fundamental theories as well as experiments. So this is a good review if you want to read about QCD as well as neutron stars. Okay, so I'm gonna touch base here, like little bit of talk about what is happening, how do we do all those things. So our goal is to measure the mass and radius of a neutron star, right? And we have to rely on some experiments, obviously, because mass and radius is something which we should be able to measure experimentally, because it is a macroscopic observable. Okay, we cannot measure it through theory. We can do in theory we can do everything, but since this is a macroscopic observable and this is related to a star, so we want to know, like we can just measure the diameter, how do we calculate the time period and diameter of a star which is very close, like, or maybe a planet? We can just measure the edges like left to right, and we can calculate the diameter, okay, and then we can use some gravitational formula and we can calculate the distance between Earth and let us say Jupiter, and we can get the R, use Kepler's law, all those things. We can calculate the mass there, right? We can calculate mass from gravitational force and all those things. It is simple. But when we talk about neutron stars, they are pretty far away. They appear like a point object, right? It is not able to see the left side or right side of those stars, and it is also have some vague properties. So we need to rely on something else. And also, when we talk about neutron stars, they are pretty heavy. When something is pretty heavy, it basically disturbs the space time, okay, and when it disturbs the space time, the light what the information through the light what is traveling to us is also manipulated, right? We have to do some correction. The fundamental example I would say is, like, due to special theory of relativity, we have this: whenever the information is traveling at the speed of light, then it has like special relativistic correction, okay, and that correction is put into the GPS map so that we can have the best time, like there is no error in millisecond as well, because whenever we are talking on the phone or GPS, doing all this GPS thing, we are communicated through the world. So we may be using a satellite based connection, the information is traveling across the world. So due to the special theory of relativity effects, the information get delayed, or there are some dilations, right? But we have to fix that dilation so that we have the correct thing from point 1 to point 2. In that case, we put theoretically the correction and we made the information adjust to that particular correction. Similarly, when we talk about neutron stars, the neutron star is very heavy and they disturb the space time, okay, and since they are very heavy, okay, let's go through this slide first. So what are the experiments that can measure the mass and radius of a neutron star? Is NICER, okay. NICER is Neutron Star Interior Composition Explorer, and it is been deployed at International Space Station by NASA, okay. This is not a video because of the PDF, but you can see the video in my YouTube video. And then we have this image. So this image tells us about something. So we have pulsars. From pulsars we can get that whenever the pulsars pulse is facing us towards Earth, then we can say, okay, there is a peak, and when it is away there is no peak. From that we can measure the frequency of that particular star, that how fast it is rotating. That is one thing, okay. But that doesn't tell us about the mass of it, that doesn't tell us about the radius of it. We have to rely on something else. But luckily we have something. What do we have is the hotspots. So in neutron stars there are hotspots, like in sun we have solar flares, we have hotspots, we have some perturbations going on due to sun's magnetic field. Similarly, in neutron star, due to its immense magnetic field, 10 to power 12 Gauss, I said 4 Gauss, I was mistaken, 10 to power 12 Gauss, which is very very high, 14 Gauss for magnetars. So when we are talking about this huge magnetic field, the particles are experiencing that perturbations, right, electromagnetically, and there are sudden burst of particle fluids and all those things. So we have hot spots on neutron star, which is different from the pulse, okay, and these hot spots help us measure something. So let us see what. So when the hot spot is facing us, obviously we will see brightness, and when it is going away, in a usual case when it is going away, like on the back or maybe this, right, the brightness becomes low, which is a very simple observation. And when it is not facing us, let us say it goes there, and then the brightness is 0, which is a very simple observation, right. But when we have neutron star, which are pretty heavy, due to gravitational lensing, what happens is, even if the hot spot is behind the neutron star, let us say this side, we also see the brightness, we also see some pulse, Why? because the neutron star, due to very high gravity, it bends the space time, and when it bends the space time, the light basically travels from behind. You might have heard about gravitational lensing. This is the sun, this is the earth, and you see star behind the sun, because the sun, due to its huge gravity, it bends the space time, and due to that bending of space time, the light follows a geodesic which reaches to earth, right? And this happens because of the gravitational lensing. So there is another example of that. If you see why the black holes doesn't look like a hole, like with the accretion disk like this, why doesn't it look like that but like this? Because due to the bending of light, this accretion disk get folded, like there is a information coming from the behind which looks like it is still an accretion disk like this, but due to the immense gravitational field there, the space time gets bent, and due to that bending, it appears like the accretion disk has folded like that, and it is facing us, but it is not true. Okay, this is one classic example of gravitational lensing. Now, neutron stars are also very dense, like 2 solar mass. 2 solar mass is lot, very high. And again I will say, so whatever information is behind, it travel through because of the gravitational lensing. And the power of general theory of relativity comes into picture now. I am not a GTR expert, I am not a neutron, I am not a gravitational wave expert. Okay, I am more into theoretical side, this is more into a experimental side. But I know that general theory of relativity, which is a theory, it gives us connection, it connects the neutron star macroscopic observable like mass and radius to gravitational lensing. From that we can calculate from the information that is coming through light. Okay, it can be X-ray, infrared, or whatever is nicer is detecting. Okay, and from that data we can analyze that how gravitational lensing impacts on the compactness of a star. The compactness of a star is the ratio between the mass and radius. So it can basically tells us about the mass and radius. So we can assume one variable and we can play with other. Okay, so by this we can know, okay, what is the mass of the star, what is the radius of the star, we can have a guess. But in addition to that, we have to also take into account some other things, like due to the information is coming from very far and it has a certain velocity, and the star is also receding or coming towards us, we have a gravitational redshift, right? Due to gravitational redshift, there should be a correction added to in GTR. Doppler shift is also a thing which should be added to the GTR calculation. So these things are very important. Then we have a Shapiro delay. Okay, the Shapiro delay is this. We know moving clocks run slow. So whenever the information, the light photon is interacting with the immense gravitational field, it runs slow. So when it gets slow, there is a time delay which is called a Shapiro delay, discovered by Shapiro. And basically when the light is traveling, due to the immense gravity of this star or maybe some other star, some other gravitational body, the time got delayed. So we have to also put this correction into that, and we put these correction into our calculation. I have not shown any calculation here, and now you can see this paper, there is a good discussion about it. So we can relate this observable, we can relate the mass and radius through the GTR, and when we have it, we can do some predictions. Okay, then we have some data from mass and radius curve. So we cannot just pinpoint one point, okay, this is the observation we had. No, we have certain uncertainty bands when we talk about experimental physics. So with the help of theory itself or majorly experiments, like scientists have put down some regions where they have confidence the neutron star mass could be. Okay, so mostly for this particular neutron star, the observation is nicer, and this is also nicer, and this was done by Illinois and Maryland group, also this. So they have put some error bar there, okay, and this was the second data was also given by for the same star from Amsterdam people. So they put a strong constraint on neutron star observable that okay, this is the uncertainty band the neutron star can have mass. Similarly, when we talk about 1.4 solar mass, which is this star particular number, okay, they have also put some constraint where the mass can be. So this is a very tedious calculation. If you want to know more, I am not the expert, you can watch some YouTube video or you can read this paper. Okay. So, but we are more interested in this particular subject here, but this particular slide is I want my equation of state, my model, my theoretical model equation of state that can explain, that can match this constraint. Okay. If I have a MR curve that fits into that curve, my goal is fulfilled. If I have a MR curve which fits into this curve, my goal is fulfilled. Okay. So, what we are trying to learn here is we are trying to construct an equation of state which fits the data, experimental data. This is our goal here. So, okay, I will stop here for 1 minute if you have any question in the slide. No question? Okay, very well. Now we discuss everything. You didn't have any question here. Okay, this someone asked me a question, but before that let me try to relate it with something. And you also asked me about tidal deformability. We will go through that, but let us discuss this very important thing here. See, let us discuss this slide. So this is a diagram. You can also see this diagram here, and I constructed this diagram, and the reason why I put it like that is because I wanted to show different part of this diagram, like which part is for which. So this is a conjecture again, this is an anticipation, this is an estimation, right, from our knowledge of strong interaction physics and from experiments. So we can get equation of state from the model, right, we will talk about that. We can try different combination of particles in our model, and we can construct an equation of state like pressure and energy density. Okay. But before that, I just want to give a rough picture that what are the different composition of a neutron star as per different sections. So you can see there is a atmosphere, there is a outer crust, inner crust, outer core, inner core. The main part of the neutron star is the outer core, where it has the most of the thing, most of the size, 7 kilometers, and density is around 2 saturation density, 2 times the saturation density. And what is the saturation density? It is 10 to power 17 kilogram per meter cube. So you put 10 to power 17 kilogram in just 1 meter cube. So you can imagine how immense it is. So this is the main part, and it basically have neutron rich nuclear matter, that's why it is called neutron stars. And then we have inner core, which is highly dense, let us say 6 to 8 times the nuclear saturation density, and radius is about 5 kilometers. And since this is the inner core, obviously the density will be very high. Okay, the more inside you go for a particular star or astrophysical body, the density is high, and there could be nucleons, hyperons, mason condensates, deltas. I would not talk about that, but we are mainly interested in deconfined quarks. Why we are interested in deconfined quark? Because we have learned that when we squeeze our baryons like nucleons or neutrons, they can have deconfined state, they can achieve deconfined state if they are close enough with high energy, right. So there is an estimation that neutron star can also have deconfined state of quarks, but this is a question. Okay, we strongly believe that it has nucleons, baryons, but not quarks, but there was a Nature paper which gives some calculation that it can also support quarks, but lot of people disagree. Anyhow, this is a science, so there should be a disagreement. And then we have all those things. If you want to know about these things more, again I will refer you to this paper. There is a particular section about it where you will learn how does these particle composition changes when we go from left to right. Okay. Now the main idea is like we have assumed different composition in the neutron star. Obviously it is not a sole assumption, it has a valid arguments behind it. Okay. And we know that there are three major parts. One is the atmosphere, which is called also no, atmosphere is just with the atoms, and then we have crust, inner crust. So we have crust. So we have two main parts, crust and core. Okay. So for different degrees of freedom, we have crust, we have different degrees of freedom, we have nuclei, we have inner crust where we have neutron, free neutron, we have outer core where we have neutron rich fluid, when we have inner core we have Mason condensate deconfined core. So you can see the degrees of freedoms are changing here, here, here. One is nucleons, then is neutrons, then is a neutron fluid, then there is a deconfined quarks or mesons maybe. So the composition is changing. So we need different models that can describe physics. The sad part is like we cannot have one single model which can explain everything. We can have, but that doesn't fit all the constraints. So we better rely on different models for different parts. Okay. So that is one thing. So that is not a concern for us right now. Our main concern is like we get some equation of state for some composition from some model, right? We have this checked. Now can we get a mass and radius from that? So from the microscopic observable, can we have a mass and radius by macroscopic observable for that? Yes, we can. So thanks to this equation we can. Okay. The TOV equation was developed by Tolman, Oppenheimer, Volkoff, and this equation describes spherical non-rotating body in hydrostatic equilibrium. So the assumptions are the star is spherical, it is non-rotating and hydrostatic equilibrium, which is not ideal. So there are TOV versions where we have rotations which is non-spherical. Okay. So there are some, but we are gonna go with the minimal example. So there are two equations, okay, pressure and mass. So we can say this is the energy density and pressure which acts like a input, okay, and this P, not P, M and R are the output. So I have written it here. So these are input, these are output. Okay. So if we put energy density in terms of radius, when pressure in terms of radius into these two equations, and we try to solve it, this differential equation, system of equation, then we get mass and radius, mass as a function of radius. Now the question arises, the equation of state we get is pressure versus energy density when we calculate it from the model. So we need to get something which gives us pressure as a function of R, energy as a function of R. But we are smart, right? We are smart people. So we can have some assumption, we can put some boundary condition and see how it happens here. So we know that from a given model we get some equation of state, and we know that in a neutron star when there will be the pressure will be maximum where? Obviously in the center of the core. So this is one boundary condition, pressure at core is maximum. And what about the other boundary condition where it should be minimum? Obviously at the atmosphere it will be minimum. So when it is minimum, the pressure is, okay, let us see what is minimum, is 0, because when there are no particles. So what is happening, pressure is going down. So we can plot it, pressure versus, come on, pressures versus R, it is going down like this. Okay. So from this property what we can do, we have pressure versus energy density. From that we can calculate PR ER, and from PR ER using this we calculate in terms of radius, and when we put that and solve this equation, then we get mass and radius, right? And this is the second part of what we are going to learn this in internship in the physics section. Now on the left hand side I am showing some equation of state that I have calculated from a particular relativistic mean field model, and for different degrees of freedom, so I'm not gonna bore you with the degrees of freedom here, but okay. And you can just relate that this is one simple curve, the pressure is maximum here, the pressure is minimum here. So this is what core, this is what crust, simple, and everything is in between. So you put that information, pressure versus energy density, and you convert it into PRER, that we gonna do in the TOV code, okay. And then you calculate the mass and radius diagram, that is the output of TOV solver. And what I get is, okay, this is the experimental uncertainty band from various experiments, and I put my equation of state there, that the MR curve from the equation of state, and I get to know that, okay, I am getting the maximum mass here. So this is the curve, okay, and this is the maximum work it is showing, and the stale part is corresponding to this, okay, the crust, and this represent the core, and this is inner core. So what is the maximum mass it can go? It can go, it fits around the uncertainty band, it is inside the uncertainty band, and if it is inside, I would say my model is successful in explaining the neutron star mass radius, okay. So this is what we want to do. Okay, now I will stop here for 1 minute before jumping to the tidal deformability thing. Okay, I guess there are no questions. I guess I have only one thing to discuss now. Okay. So before discussing tidal deformability thing, let us discuss about neutron star mergers. Okay, so mergers are basically, obviously from the name, merger is like the two neutron stars are merging, like they are colliding and eventually they merged. So they are in an in spiral phase, they collided with each other here, coalescence phase, and they eventually ring down to a single neutron star. Okay, they can also become black hole, that's a different story. So there are three phases: in spiral, coalescence, and ringing down phase. So now the thing is, whenever two gravitational bodies are rotating across each other, around each other, since one thing we have to understand is the matter is not solid. It looks like a solid, but when it is in an immense field, it could be gravity or something, it acts like a fluid. Okay, so let us say, let us take an example. At the core of the earth, the iron is an atom, metal, solid, but due to heavy high pressure it acts as a fluid like plasma. And similarly, when we talk about the system of earth and moon, so moon basically, earth basically feels the gravitational field of moon, and it shows the tidal deformability. You know that we get tides, earth get tides, not we get tides, again I said we. So earth get tides every day, and whenever the moon is closer to the earth, the tides are very high in height. Okay, so why this happens? Because of the gravity. Okay, so we can relate it with that. So the two systems are basically interacting, they are rotating to each other, and let us say this is earth, this is moon. Okay, earth, moon also feel tidal deformability, but it is not visible, it is very less. One thing is, it doesn't have fluid on it like a real fluid like water. Earth has water, so we can see the tidal deformability. Okay, so when we talk about neutron stars, we have two neutron stars rotating around each other, and they have fluid, like they have like super fluid, strongly interacting. That is not solid, that is like a plasma in immense strong interaction field. Now they are rotating each other, and they are experiencing this, let us say they are not rotating each other, they are steady, and they will be attracted to each other, and because they cannot lose their identity itself, it will be like something like this. It will be deformed. I am not good in drawing, but it will be something like this, right? So they will feel this bulge towards each other because of gravity. But you have to assume that it is elliptical. Okay, but they are also rotating. If they are rotating, there is a delay, and due to that delay there is a lag, and due to that lag the center of bulge doesn't point towards the exact center of the other star, but it points away because there is a motion. Okay, there is a delay, there is a inertia, and due to this process, this whole process, and the gravitational whenever the two stars are colliding with each other, basically what they do is they disturb the space time. When they disturb the space time, because basically the information is carrying through what? It is carrying through the gravitational wave, as a gravitational wave, and when it reaches earth, we detect it. Similarly, tidal deformability, this whole process also disturb the gravitational space-time fabric, and eventually it travel as a gravitational waves. So it has that information, that tidal deformability has led to some correction in the gravitational waves, which can be calculated experimentally using LIGO, which is a different story. Okay, so from this information we can get a curve. Okay, so far we have got this curve, we don't have any information about this curve, and by analyzing this curve we can try to relate, okay, what was the strain amplitude of the inspiral phase, and how can we relate it to the original star. And these are the constraint from the equation, not from the equation, from experiments, that gives us a huge constraint, right? You will say it is not a constraint, it is very wide. Why would we say it is a constraint? But from today's LIGO data, this is the best we can do, and I think it is enough for a start. And with the modern machine, with the modern LIGO machine, like when we have a very high sensitivity, it can sense very high, very minute gravitational waves, which signal to noise ratio is very good. Okay, then we can have better explanation of this curve, and we can tell better what happened at the coalescence phase, merger phase, or what happened at the ring down phase. So that is still under exploration. And to calculate gravitational, not to calculate, to observe gravitational waves effect on earth, we have LIGO. Okay, so I think I have explained it well in my video, I am not going to do that again. And we have LIGO interferometer gravitational wave observatory in India, which has been improved, and it will be there. So if we are looking into gravitational wave physics, this is the opportunity. You have to talk to people who do physics in that, and try to collaborate with them, because in next 10 to 20 years this will be a significant area of research, and India is heavily investing in that. So IOCA is one of the partner, RRCAT, and this is the natural national body. Okay, so I will stop here, and if you have any question, please do ask me. Okay, so I hope I was able to clear your doubts. Okay, whatever you had in your mind. If I have missed something, please let me know. Okay guys, so whenever you feel like you are still disconnected, go watch the video again, per particular parts. Maybe I have not put the keyframe, what you call it, I forgot the name of it, when you do the sections in timestamps. Yeah, I have not put timestamp, I can do that sometimes. Okay, so so that was one part of our today's session, right? And I really want to discuss physics with you. Today is the day I am very happy that we discussed, and we are ready with all those artillery that we can deploy, artillery. And now this is the PDF that has more or less the same information what I gave you today, right? It is about the my video, my PDF. Okay, you can have that, you can read from that. It doesn't contain each and every piece of the information, but it has mostly the main highlights, so you can go through that. Okay, so these notes are available to you. Okay, I would like to also discuss something else. So before that, I want to discuss this. Before that, I would again stop for like maybe 1-2 minutes, and if you want to take a 5-minute break, let me know, because we have to touch this thing today, otherwise it will be too difficult for us in the coming weeks. Do you want to have 5-minute break or not? Just tell me, hands up, hands down. I can talk for hours, I don't mind. Okay, most of the guys don't want. Okay. Okay. I'm actually having a problem here. When I'm sharing screen on my computer, maybe I can just disconnect this video recording and start again.